Hi guys, we're back today talking about star clusters, and we're going to answer questions number 25 through 30 in your packet, so that will finish that off. Let's dive back in here with a little refresher again about what a cluster is. So a cluster is important to all this because a star cluster is a group of stars that all formed at the same time. So they are in essence the same age. They're the same composition, the same distance from us, but that since they all formed from different amounts of gas as the cloud of gas and dust collapsed, they're different masses. And if you remember back to earlier on in the presentation, we talked about how mass is the main thing that determines how a star evolves. So remember, larger mass stars burn out faster. They live their lives quickly, and then they evolve off the main sequence. Smaller mass stars, lower mass, live quite a bit longer. And those numbers are pretty well fixed. So what a star cluster represents to us is a whole bunch of stars that all formed at the same time out of the same stuff, but they're in different stages of their lives because some of them have already gone out, some of them are getting ready to, some of them are just hanging large on the main sequence. So we're going to use something known as this turnoff point to help us to understand how old a cluster of stars is. So I guess I should also say this. Star clusters exist throughout our galaxy. So I'm talking about clumps of stars that are in the Milky Way and in the area out around what you would probably think of as the Milky Way. So we'll kind of come back to that again here in just a second. But let's dive into the turnoff point. So the main sequence turnoff. If this is a main sequence, this is an HR diagram again for you here, and it looks a little busy and a little crazy because there's a whole bunch of lines mapping out the evolution of different types of stars off of the main sequence. So that's nothing new. We've talked about that. What we're going to use this for is if we plot all of the stars in a cluster on an HR diagram, we're going to see some really unique patterns develop that will give us precisely the age of the cluster. And you can think of it like this. Young clusters are still going to have a lot of massive stars in the upper left-hand corner on the main sequence. Okay, that's what MS means there. Older clusters, those massive stars have already moved off the main sequence. Maybe they're red giants, they're supergiants now, but they're no longer on the main sequence, so we're not going to see stars on that part of the main sequence in the HR diagram. Okay, so the further down we see stars on the main sequence still, the older that cluster is. If that makes sense. I'm going to give you some examples here, and then we'll try and make an easy way for you to answer this question here, because the question is to describe how astronomers can tell the age of a cluster by using the turnoff point on the HR diagram. That's number 25 on your packet. So here's a nice diagram. It's stages going from A through F, so it starts from the top left side of the screen there, and we have a zero age cluster. So this is a cluster where all of the stars are still on the main sequence, and that's what that white line is there. The yellow dot is, of course, at 1 solar mass, which, of course, would be our sun, right? So it kind of gives you a clue as to where we are in the main sequence when we're talking about these things. If you look at the B diagram there, that's at 4 million years. So after 4 million years, stars that are kind of nearing about 20 solar masses are starting to evolve off the main sequence, and you can see the top of the main sequence there is kind of twisting off to the right and curving back a little bit. So those stars have left the main sequence. Some of them are zigzagging as they change in their properties and evolve. If we go over to C there, we're now at 10 million years, and we're a little further down the HR diagram where the evolution point is getting a little closer to maybe 15 solar masses. Okay, as we move on to D, we're looking at 100 million years, and now we're at those stars that are around like maybe 10 solar radii, I guess there. I'm not sure why they changed the units, but we're moving off the main sequence. As we continue down, we'll go through 1 billion years, and then if we look over there at 10 billion years, we're right at about the point that our sun is. So our sun will evolve off the main sequence in about 10 billion years, And if we were looking at a star cluster that contained our sun or something similar to our sun, and we saw the turnoff point right there, we would know that the cluster was about 10 billion years old. So you can see the further down you go on the main sequence with the turnoff point, the older the cluster is. Hopefully this is starting to make a little bit of sense. Let's look at a few more though. So here's two examples. Here's the Pleiades that we mentioned before, and we looked at some photos there. If you haven't seen the Pleiades, you should go out in the sky tonight, take a look, get an app on your phone. It's a very beautiful constellation, but it's also a star cluster. So the Pleiades is about 100 million years old, and if you look at the diagram there for the HR diagram, there's no hot stars there. Okay, at the very, very top left-hand corner of the diagram, there's no really, really hot stars. Okay, so it's not that old. There are still a lot of stars. I know 100 million, 100 million years old is pretty old, but it's not that old. So if we look over here to the globular cluster, M55, it's 10 billion years old. So billions, not millions, 10 billion years old. It's considerably older. If we look at its main sequence, there's no stars at all. Like at the top of the diagram, even in the middle of the diagram in the main sequence, everything has evolved off down to like right there, kind of in the middle of the main sequence there. It's all slipped off into the red giant region of the HR diagram. So you can see the differences there. Let's follow through just kind of a little flip book here that I put together. So here's a star cluster. It's at 0 age on the main sequence, so there's a bunch of high mass upper left hand corner of the main sequence, and the low mass stars, the really, really cool red dwarfs, they're not even on the main sequence yet, so they're still evolving onto the main sequence. It takes them a long time to fire up fusion, and they're really slow at it. So they're kind of moving towards the main sequence right now. That's why that little tail is up there and off to the right. The black dots are the stars, if you will. Okay, so let's move forward in time. As we move forward in time, some of those upper mass stars leave the main sequence. They become giants, right? They're ending their lives. Now we'll continue forward here. We're at 10 to the 7 years on that picture. Now 10 to the 8 years, a few more stars have left the main sequence. So the turnoff point is the stars that are still right where they're still on the main sequence. And if you look over there to the bottom right, you'll notice that a bunch of those red dwarfs have made their way onto the main sequence. So that's happening too as we're moving forward here in time. Let's move forward again. 10 to the 9 years now, main sequence is still, the top of the main sequence is still trailing off there towards the giant stage. And now let's move to, we're at 5 times 10 to the 9 now years. Even more stars are peeling off. So with the last one here, we're looking at the stars as they've peeled off there towards the red giant branch. There's a little bit of horizontal branch stars there. We talked a little bit about them. White dwarfs are now on the picture, if we can see some of those. So some of the stars have completely evolved from red giants all the way down to white dwarfs. The turnoff point on the main sequence gives us the estimate of its age. There's the turnoff point right there. Okay, so if we know that turnoff point and we know what size stars we're talking about there that are on the turnoff point, we can know how old the cluster is. Okay, so let's kind of revamp that again here. Describe how astronomers can tell the age of a cluster by using the turnoff point. Okay, so there's a couple pieces to this. First of all, we have to recognize that stars leave the main sequence. The highest mass stars leave the sequence first. So those are in the top upper left-hand corner. So if we just look at what point of the main sequence there are still stars on, we then know that's the turnoff right there. We know how old the cluster is because lower mass stars take longer to leave the main sequence. That's essentially the answer to the question there. So throw that into your own words there, however you can do that. All right, let's kind of move on here and we'll describe clusters a little bit. So there's two types of clusters that we're going to talk about. And these exist in our galaxy, right, the Milky Way. The first type are open clusters. Okay, so an open cluster is like the Pleiades. Here's a beautiful picture of an open cluster here. These stars all formed at the same time, right? So that's what clusters are. Open clusters are anywhere from like 10 to a few thousand stars in about 25 parsecs. So that's just kind of a measurement of the volume we're talking about here. So in comparison, there's not many stars in an open cluster. So if you're writing things down, open clusters don't have as many stars in them. Also, open clusters contain a lot of young to middle-aged stars. Okay, the oldest ones are only about a few billion years old. That's not very old when you're going to compare this to the other type of cluster. So open clusters are unique in that they are filled with young stars, and there's not as many stars there, and they also form in the disk of our galaxy. So when we talk about the Milky Way, you know the Milky Way is a disk shape, kind of like a pizza, and we're moving around that disk as well. Well, there's clusters of stars that have just formed in that disk, or haven't formed that long ago in that disk, and these are still forming today. There's about 1,100 of these things that have been discovered, somewhere around that range, and so they're still forming today. So keep that in mind. We had a couple pieces there. They're still forming today in our galaxy, the Milky Way, in the disk. There's not as many stars in them, and they're young. Okay, they're called open clusters, by the way, because the stars are spaced far apart in them. Okay, and eventually, what will happen to these stars is they'll continue to move apart, and the cluster will spread out. Okay, as it ages. Let's turn now to globular clusters. Okay, these are shaped like a globe, hence the name, right? They're they're spheres. Now, in terms of size, they're roughly about the same size as the open clusters are. Now, the difference is they contain 10 to the 5 to 10 to the 6 stars in that same space, or a little bit more. So these things have way more stars, like way more stars are packed into the same space. With those stars in that space, they're not actually spreading out, like they're not moving apart like the open cluster is. These stars are actually orbiting all around each other in sort of some very chaotic motions. It almost looks like a bunch of dust particles moving around in different directions. And the distance between the stars is very small, so it's only about a few light months apart, so they are really packed in close together. Now don't worry, they're not colliding with each other or anything like that. Their mutual gravitation, the pull from all of the stars kind of combined, is keeping them from colliding, but they are all orbiting sort of that central mass there in the middle in different various directions. So what's unique about these, other than that there's so many more stars packed into about the same shape, and that's shaped like a sphere or a globe, and the distance is not very far apart, these things are old. They're like somewhere around 11 billion years old. That's old. That's like not long after the formation of the Milky Way kind of old. These are indeed the oldest objects in our galaxy. Now where they're located is also pretty telling. They're not in the disk, and we haven't talked about this yet, but the Milky Way, the disk portion of our galaxy, is just a very small portion. The larger part of our galaxy doesn't really look like a whole lot, but it's a gigantic sphere that encompasses that flat pizza disk that's in the middle of our galaxy. And that outer portion of our galaxy is known as the halo. Now the halo, it's humongous, and these objects, these globular clusters, are orbiting around the center of our Milky Way. So some of them are actually passing through the disk. Some of them are parallel with it, lined up with it. Some of them are way outside of the disk. So they're orbiting our central black hole is what they're really orbiting. In fact, we use globular clusters to determine where the location of the center of our galaxy was. That's how we know where that black hole is at, that supermassive black hole in the middle. It's from these guys. So they tell us a lot. They tell us about essentially how old our galaxy is, but how do they form? So that's a good question. These things are not currently forming, not very much. We have discovered a few galaxies where there's a few of them kind of popping up, but the thing is they formed during the early formation of the galaxy itself. Back when there was a lot of gas and dust still available, these things gobbled it up. So that's why they're some of the first things in our galaxy. Now there's not as much gas and dust available, and so they're not forming as much. And that's pretty much about it. Oh, there's about, in comparison, I said there was about 1,100 open clusters. There's only about 150 known globular clusters out there. So quite different than the open clusters. Each of them tell us something about the history of our galaxy, right? These things tell us about the ancient history. The open clusters tell us about the more recent history. All right, let's kind of move on now to some pulsating stars. Not all stars are stable. Some of them vary in brightness, and it's not due to something moving in front of the star. In other words, what we would call an eclipsing binary. Those things do exist, but I'm trying to talk about stars here that pulse, that vary in brightness, not because something passed in front of them. Okay? So let's explain kind of how this happens, at least in maybe one case. There's many cases where this can occur, but by and large, you can kind of look at them all in terms of a type of star known as a Cepheid variable. So first of all, these are really important stars because we use them to measure distance. It's very difficult to measure distance. Distance is probably the most important measurement that astronomers make. And we can use Cepheid variables to measure distance because we know how bright they're supposed to be based on how fast they pulsate. So they're a very specific type of star, and we think anyway that we understand how they're made and what they are well enough that we can make estimates of distance to them. So these things exist not just in the Milky Way, but in distant galaxies. So we're using these stars and galaxies that are way, way far away, way outside of our own Milky Way galaxy to figure out how far away those galaxies are. Galaxies that are so far away, there's no way we could use parallax to measure them. Remember when we measured parallax? Okay, so why do they pulsate? So some stars will start to pulsate when they pass through what we call the instability strip. Okay, and it's fairly complex, and I'm going to try and explain it to you. But in essence, you can think of it like this: as a star is fusing its nuclear fuel, right, and begins to run out, it starts to collapse, which then causes the core to heat up, which expands the star. If the star expands too much, it will cool too much on its outer layers, and it will cool the inside a little bit, and it will start to collapse again, which will then heat it up, which will expand it, which will then cool it off, which will cause it to collapse. So there's only very specific regions on the HR diagram where this instability is kind of possible, where the right combination of temperature, pressure, gravitational force is just right, that it kind of pulses in and out. The star expands, the star contracts. The star expands, the star contracts. And that's what gives us a pulsing star. So if you want to write something along those lines, that would be perfect. So let's see an animation here. Here's animated of a spiral galaxy, and there is a Cepheid variable star there. There we go. So these things pulse anywhere from tens of years to decades between pulses. So this is pretty fast here, but they can take a long time to pulse in between the pulses. But it's at least in terms of human lifetimes, we can measure these things. All right, a little bit more here, a little bit more description. I know I mentioned this already, but you can see the HR diagram there. There's some strips there called instability strips, and as a star passes through that, it will pulse, very likely pulse. It can move out of that and stop pulsing and then move back into it again, depending on the track it takes as it leaves the main sequence. But essentially, you can describe the answer to this question by saying, certain combinations of size and temperature cause a star to be unstable, right? And as I said, the star, as it runs out of fuel, contracts and it heats, and then that causes it to expand. Expansion cools the outer layers of the star. The star collapses again, contracts, heats up, expands again, and then that pulsing motion happens. So you can see that there in the diagram. I wrote it again here, a little bit more complex description, maybe more than you really need to know, but it also has to do with the ionization of gases at the surface of the star. If electrons can attach to protons, It's very different than when they're ionized. And the when they ionize, they lose energy to that. Okay, and then when the electrons attach back to the atoms, that changes the whole scenario again, and that kind of causes the star to overshoot its equilibrium stage and then contract back down. But that's probably more information than you need to know to answer that question. All right, let's move on here to some binary star systems. As you found out already from the video, binary star systems are actually quite common. They're more common than solitary star systems. In that sense, our sun is unique in some respects, and there's plenty other solitary star systems out there, but binary star systems are more common, and they can evolve very differently. So I guess you can answer this number 28 here. The most stars, what is a binary star system, and are they more or less common than ours? Well, a binary star system is when you have a pair of stars orbiting each other. So imagine two suns, and they are more common than our stars, single solitary stars. Okay, now let's talk about the evolution of these star systems, because it can be quite different than what happens to a single solitary star. So in a binary star system, more than likely one star is bigger than the other, and we know something about bigger versus smaller stars. Which ones evolve first? The bigger ones, right? So if you look at my diagram over there on the left, you'll see there at step 1, the larger star, star 1, evolves off the main sequence first. It expands into a giant. Now, if you look at that little hourglass sort of shape, that's describing what's known as a Roche lobe. So that's basically the gravitational forces that are existing between the two stars. So those stars are orbiting each other, and as that large star on the left, star number 1, expands, it can get so large that it actually fills its Roche lobe. Now, if and when that happens, it's going to start to transfer material onto the other star, which is going to increase that star's mass. So this thing's going to change quite a bit as it goes. The material there in step B step C starts to flow over onto the other star. If that other star gobbles up enough of that material, you'll end up with kind of an early white dwarf on the left there in star D. So the star that's on the star 1 has evolved off the main sequence more rapidly than it would have. And if we look over there at the star on the right, star number 2, it's now become a blue star. So it went from being sort of yellow, maybe like our sun, to being a blue giant star. It's now further up the main sequence. It hasn't left the main sequence, but now it's got so much mass that its evolutionary fate is far different. Its life expectancy is now much less, right? Because it's going to be fusing a lot faster. But remember, it didn't evolve off. It's still fusing hydrogen down in its core like it was doing to begin with. It's just now fusing faster. It's got more material pushing down on it. Its gravitational force is a lot stronger. So we've got our star on the left there that's become a white dwarf. It's lost all of its outer gases to the other star on its right, caused the star on its right to expand into a blue supergiant, and now it's going to evolve more rapidly. Okay. Now, as it evolves, it will expand, right? And as it expands, it's going to start dumping material back onto the white dwarf. Now, here's where stuff gets interesting. So, as it dumps that material back onto the white dwarf, some couple of different things can happen. Okay. The first thing that can happen is called a nova. So we've got a white dwarf that's now collecting material on top of its electron degenerate matter. So material is filling up, gases are filling up on top of this core of this dead star. If those nuclear reactions start and fire up all at once on the surface of that thing, it will light up for a few hours and be like 500,000 times more luminous than the sun. These things are very bright. We can see them very far away. Okay, so a lot of these outbursts are separated by thousands of years. Some erupt like every decade or so, but they'll repeat because every time more material fills up on the outside of that white dwarf, it'll explode again. Now notice it's not destroying the white dwarf, it's just blowing up the material that's on its surface. So more material gets dumped on, it flashes and it novas again. Okay, so let's look at our questions here. How do binary stars evolve differently than a single star system like our own? Well, the difference is that as one star evolves, it starts to spill mass back onto the other star, causing the evolution of those two stars to be very different, right? And then as the other star evolves, it will spill mass back onto the original star. So it can be quite different than what we see. Now let's talk about another fate. So that was a nova, where that gas explodes on the surface of the star, ignites nuclear fusion all at once. Now let's talk about that white dwarf, because if this continues long enough and enough material keeps getting added to that white dwarf, eventually it's going to exceed a certain mass range. It's going to get too much material built up on its surface, and it could go supernova. So these are specific types of supernovae explosions known as a type 1a supernova, and they are really bright. So these things can be as luminous as 10 billion suns. Okay, and they're so bright that we can see them across vast distances of the universe. Now the reason they're so bright, if you picture this, essentially we have a naked white dwarf. It's not cloaked in any gases. Material is spilling on top of it, and it exceeds a limit known as the Chandrasekhar limit. And that's a limit that was proposed by a famous Indian astronomer, Chandrasekhar. And he discovered essentially how massive something had to be to overcome electron degeneracy and collapse into a black hole. So that can occur with a white dwarf like this. So if it's about 1.4 solar masses, 1.4 times the mass of our sun, this can occur. So the material gets dumped on the white dwarf, pushes it over that limit, and now instead of just those outer gases exploding, the entire star explodes. It goes supernovae. And nothing is left behind from this explosion, right? It could collapse into a black hole. It could just obliterate the star entirely. But it's completely destroyed, leaving the other star that was spilling material over onto it to just kind of evolve on its own. Now we can kind of tease all that stuff out. We can figure out, based on orbits and things like that, if there's a remnant there or if the star is gone supernovae, something like that. But anyway, you can now describe there for number 30 what a type 1a supernovae is. It is a star. It is a white dwarf that has had its mass limit exceeded by material from its companion dumping on top of it, and it has gone supernova. Okay, and that is it, I believe, for the rest of this. So you guys have a good day, and you can now submit your packets.